Welcome back. So at the end of the last video, I asked you, how does this proof of the derivative of an inverse function formula really use the fact that the inside function g is continuous at the given point? Now it's buried in the argument that really appears in the proof of the chain rule, and that's the argument that this limit here, the limit of f of g of w minus f of g of z over g of w minus g of z, that limit really yields f prime of g of z. That proof references, I indicated that that was the same as the proof in the chain rule, and it is, but the chain rule relies on this property of limits, which I call the composition law for limits. And this property allows you to move an outer function inside or outside of a limit, provided that the outer function is continuous, and calculate, therefore, the outer function evaluated at the limit of the inner function. So in this context, the outer function is actually this difference quotient function, f of u minus f of alpha over u minus alpha. That's the outer function. And the inner function is simply the function g. So the outer function is continuous because f is differentiable, but the inner function has to have a limit evaluated on it. It has to have a limit where w approaches z of g of w, and that has to yield g of z. So the continuity of g at z is buried here in the assumption that the limit of g of w as w approaches z is actually the same thing as g of z. And that's how we used the continuity of g in this proof. It may seem like a very technical fact, but it affects the differentiability of some very, very important complex functions, which are expressed as inverse functions of other functions. And it turns out that those functions cannot be made differentiable at, where you might expect them to be differentiable. And the fundamental reason is they can't even be made continuous there. So that's how we used the continuity of g in this proof.